All right, now we're going to talk about the case where we have constant acceleration. So what we're going to do is acceleration is equal to some constant number. Why that simplifies it, and that happens a lot in the problems that we do, is that acceleration is constant over a certain period of time. So what we're going to do is a little bit of calculus here. We remember before that the velocity is the derivative of the position versus time, and acceleration is the derivative of velocity with respect to time. And what that means is I can plug that in for the velocity and say, oh, well, this is just d dt of dx dt, because that's what velocity is equal to. What that says is that this is the second derivative of the position versus time. Okay? So, when we do this, or when we want to figure out how much we have here, we're going to start with here. So what I'm going to do is use this equation. The acceleration is the derivative of velocity with respect to time. To analyze this, what I'm going to do is I'm going to multiply both sides by dt. This becomes a dt is equal to dv dt. I mean, see, just dv, because those cancel out. And to get rid of the differentials, I have to integrate them. I have to integrate both sides. But when you integrate a constant, you can pull the constant out front, so this becomes the integral of a dt, integral of dt, and the integral of dv. Well, this is the easiest integral in the world. This is just at plus a constant, because it's an indefinite integral, and this side is just velocity. Now you can say there's a constant over here, but we can combine them into just one constant here. And then we can figure out what that constant is. If we set t equal to 0, then we can say that the initial velocity is the velocity at v naught is the velocity at t equals 0. So this is going to be the initial velocity. So what I'm going to say is if t is 0, this term goes away, and the constant just becomes v. Well, we know that the velocity at t equals 0 is just v naught. So I can plug that in for the constant. So what I get is this, is that the velocity is just equal to v naught plus at. So, what that says is if we have a constant acceleration, that the initial velocity is going to change by how long we're accelerating. The time you accelerate is going to change the velocity. Remember, the sign can change, so it can go up or down. But the velocity change is just equal to the acceleration times the time. Now we're going to go up to here where we say that the velocity is equal to dx dt. And I'm going to perform the same thing. I'm going to multiply by dt. I'm going to get v dt is equal to dx. And then to get rid of the integral, or the differential, I'm going to integrate. And so this becomes, now v is not a constant, but I know what v is, so this becomes the integral of v naught plus at dt is equal to the integral of dx. So all I did was substitute for v into this equation. Now I'm going to do this in two parts. So this is going to be the integral of v naught dt plus the integral of at dt is equal to the integral of dx. So all I did was distribute this. When I do that, v naught is a constant, so that pulls out front, and we just have the integral of dt. This just becomes v naught times t. Here we know the acceleration is a constant, so we're going to pull that out front. But now we got the integral of t dt, and this integral of dx is just x. Now the integral of t dt, remember when you take the integral of a function, t as a function of this, the power, you just raise the power by 1 and then divide by that power. So in this case, it's t as a power of 1. We're going to raise it to 2 and then divide by 2. So this becomes v naught t plus at squared over 2 plus a constant is equal to x. And when I do that, I'm going to play the same thing where I say if t equals 0, this is 0. If t equals 0, that's 0. And x is just the initial position at the time t equals 0. We're going to call that x naught. So I'm going to get the equation x is equal to x naught plus v naught t plus 1/2 at squared. All I did was rearrange the equation above it. So that we now have two equations. Remember, these only work when acceleration is constant. There is one more equation, so I'm going to rewrite these because I want you to have these because we use these a lot. In fact, we use them the whole semester, so make sure you keep these in mind. We have v equals v naught plus at. I'm just rewriting that one. Then we have x is equal to x naught plus v naught t, plus 1/2 at squared. And then we can do another one if you want. I'm not going to do the math, but if you are a math student, you feel like it, you solve this for t, then you plug that back in here for t and t. Remember, you have to square it, so it gets kind of complicated, so it's kind of a long problem. But then you combine all of it together, and you get a new equation, and you get that v squared is equal to v naught squared plus 2a x minus x naught. So these three equations are what we call our constant acceleration equations. And that we use whenever the acceleration is not a variable, meaning it stays constant during the time interval that you're doing this. So these equations we use a lot. We don't use the calculus version. If acceleration is changing versus time, then you can't do any of this. You have to do it using calculus. All right. So that's how we derive these equations. Now we're going to do some problems using these kind of equations.